to you if you were at the SMPC by any chance. So I'm going to talk about, trying to get a better understanding of the role of features in emotion recognition using a new data set that we have called the MAP dataset. Stands for Music, Affect, and Physiology. So, as we know, the area of music and emotion has been extensively studied. And a lot of this work is in this area of predicting and classifying emotion. And there are different ways that it's being done. One is taking features directly from the music content itself, so you can audio features, etc. And then you can use those to come up with some kind of a prediction function. Another thing is trying to find or capture physiological activity patterns. So people listen to music, they have responses to that. You can ignore the music and just look at their physiological responses alone and see how that's associated with emotion during music listening. And one other approach is you can combine both these features together, both the musical content as well as the physiological activity, and you have richer features. So in our previous work, we've used basically neural network models, and we've taken audio input features from the music directly, and we've been able to predict emotion of human listeners with some degree of success. We've also been able to ignore the music completely and only look at the physiological responses and then use those to be able to predict emotion. But the third approach, which we found was more powerful, was you can do some kind of an ensemble combination where you can have a trained network with just audio features and a trained network with just physiological responses, and then you can get a richer prediction. And then when you combine them using what we call committee machines, you can also, it might also have some theoretical value, like, from a computational modeling perspective. You can see in which situation which seems to contribute more. Is it the physiology? Maybe that's a reflection of many things about the person. Versus the music, which is much more of a universal thing. Like the musical content is not going to change no matter who the listener is. So far, we've primarily predicted global, or what we call aggregate, emotion judgments. So a listener listens to a piece of music, an entire piece, and then he or she is asked to rate the emotion. So they'll give you some kind of a summarized emotion. That's what we refer to as the global emotion. But you also have continuous emotion ratings, where as the piece evolves moment to moment, emotion also changes, and there's something valuable in that too, in trying to predict that. So here our focus is only on the audio or the symbolic features side, which is the music side of it. I'm not going to talk about the physiology aspect. And what we want to know is, how do these features contribute to emotion, both in a global prediction context as well as in a continuous emotion prediction context. So this is probably something that connects with me personally, and this has always been a theme, and even for us, CogMIR, it kind of relates to it. And this is a very broad kind of way of looking at it, I'll say. So if you look at the music cognition community, roughly, I guess, and if you look at the MIR community on this end, you can say that, computationally methods are probably increasingly complex as we go more towards this end. And the reason being, there are performance-related criteria here. So better methods means better performance. So on that end, I'm talking about something more linear, along the lines of correlation, multiple linear regression. Here I'm talking about, as you keep increasing, everything from support vector machines, both regression and classification, to recurrent neural networks with dropout, as well as Bayesian hierarchical networks or deep belief networks that use MMCCs, etc. So Now these methods are clearly working well, but from a computational modeling standpoint, if you had a linear method that worked really well, then it would actually be very powerful because you could interpret it more. What is the psychological or the cognitive relevance of those features? And from a modeling perspective, that's what we are interested in. So yes, we're interested in great performance, but we also want to kind of track what these features mean. So to do so, we want to kind of marry these two approaches and do something that is a nonlinear method but still doesn't go too far off of our ability to interpret them once we have a trained solution. So this is where I'm going to talk about the data collection. As I said, we are referring to it as the map data set, and probably in, I would say, 2.5 to 3 months we should have it released. That's our hope. We have collected 60 excerpts, so that's a big difference from the previous data sets that we've been collecting, which is much smaller, like along the lines of 12. And earlier, the problem was you cannot generalize once you have a small data set, and now we have a bigger data set that spans across 4 genres. Not quite big data, but it's rich data. Yeah. One of the reasons why I call it rich data is because of what we captured here. Not only is it across 4 genres, but one way we thought of this is not time-bound, excerpts like 1 minute, 30 seconds, but 32 bars. So that's what we decided. So here we wanted to think of each moment not as a moment-to-moment kind of distinction, but more as a musically relevant chunk, like a bar to bar. So that's how we are looking at the evolution of music. We're capturing continuous emotion ratings in here, or rather we've already captured, which is a big difference from our previous experiments. We are also collecting participant physiology, so that's what we've done. So while a participant rates, he or she was also listening, and was also hooked to 5 different channels of physiology. We're collecting emotion along the standard 2-dimensional valence and arousal scale. So valence going from pleasant to pleasant, arousal from calm to excited. So the way the experiment was set up is each participant listens to 12 different excerpts here. Everyone has a randomized order, and each one listens to not at least, but exactly 3 in each of these 4 genres. So by the end of the experiment, you would have each excerpt heard exactly by 12 different people. So each excerpt received 12 unique listens. And it was in the order of white noise, music, silence, followed by white noise, music, silence, etc. So what I'm showing you here is basically a mean of all the means. So for each excerpt, you have a continuous rating. So you can take an average of that for each participant. Look at the 12 participants who heard that particular excerpt and take an average of that, and that's when you get this. So 4 genres. The ones in red are metal, and then you have blues, pop, R&B. And you can see how they're generally spread out along the valence and arousal axes. So you'll notice that metal is the one that has more of a negative valence contribution here, and the other 3 are more or less across these 2 quadrants. So now, how we actually did our emotion prediction. So I'm using simple multi-layer perceptrons. So it's a neural network with just one hidden layer. And I'll get to why I'm using only one hidden layer. In terms of what are the audio features we're collecting. So since we're clearly not taking something very low level, like say Mel frequency capsule coefficients, and trying to learn features in an unsupervised way, our features are much more higher level. I would say low-level audio features, acoustic features to mid-level musical features. Now, there's plenty of work done here, in terms of what are relevant features. Mary had referred to a few. Here is a table that I've lifted straight off of Eric Schmidt's PhD dissertation, which is an excellent summary, actually, of, and it actually captures a lot of studies that I've done, and that tell us what are some important features and what do they really, what's their importance in terms of what they capture from the music. And these are all very relevant to emotion. So there's plenty of studies that went into this. Irola and colleagues, Mion and Dipoli, Laurier et al., and many more. So based off of that, we narrowed down onto 12 different features. So some of these, again, would paddle, what Mary mentioned. So RMS, that's global energy of the signal. Low energy, which is the percentage of frames that are less than the average energy. Even density, so that's how active the song is, the number of note onsets per unit time. Tempo, everyone's familiar with that. Pulse clarity, that's an estimate of the rhythmic clarity. Spectral centroid, of course. Roll off, that means the frequency below which 85% of the total energy is contained. Brightness, that's the amount of energy that's over 1500 hertz. These are the measures we use, actually, basically. We didn't change the defaults from MIR toolbox, which is what we use to extract the 12 features. Inharmonicity, which Mary referred to, the amount of partials that are not multiples of fundamental frequency, and mode, of course, how major or minor it is. So all these features were extracted from these 60 excerpts, and I did a 5-fold cross-validation, so that gives me an 80-20 training versus testing split. And all the features are normalized. Weights are initialized to some random low weights. And for each excerpt, it's just a feed-forward network. You find the error. This is supervised learning, clearly. Thanks to Sebastian. Thanks to Sebastian, right?
Yeah.
Thanks to you for giving that overview on unsupervised and supervised. I don't have to explain what I'm doing that much here. But basically, we know what the ground truths are for arousal and valence. So with every input, the network spits some value. We get the error. We backpropagate the error using gradient descent. And the cycle continues with every other excerpt. Once the epoch is over, you continue training it until a certain convergence, satisfactory error convergence has occurred. So my measure was mean squared error of less than 0.015. Another thing is the units, the number of hidden units. So initially I started off with a slightly larger number, but there's always the tendency of overfitting, especially for a small data set. So I tried to bring it down as much as I could without losing the performance, and I could finally bring it down to something like 3, so that just to know that that could improve generalizability of the network. Okay, so here I'm showing you just to give you an idea of what I'm tracking in terms of performance. The ones in black are the ground truths for 2 different excerpts, E30 and E5, and the ones in red are the network predicted values. And this is from the training sets for those networks. So which means the network never saw those until it was trained. And then after being trained, these are the values we got. So there are 2 things we can do in terms of tracking performance. One is we can track the Euclidean distance between the actual and the network predicted, provide that as an error measure or convert that into a performance measure. And we can also do the standard root mean squared error. So with both these, we get reasonable values. And once I saw some consistency across the networks, then, and this is the key part, this is where the modeling aspect comes in. What can we do once we have these trained networks? So one thing we can do is we can take each of these features as you for a trained network and knock off each feature. If you knock off each feature, then you'll see how much the performance is degraded, and then you can rank, the importance of each feature based on how much the performance is degraded. One downside of that is you lose the sign. which direction is it contributing. Another slightly better method, or more sophisticated, is you can look at the weights themselves. So for each feature, you can look at what is the weight contribution from this feature to the output, whether it's arousal or valence, and then what is it as a proportion of all the other feature contributions. And you can also retain the sign that way. So this is what we have for the global ground truths, basically the global emotion assessments. And you get these features and their directions, and you can see things like mode clearly for valence. You also have other things, event density, and then for arousal, event density is in the other direction. So you can kind of expect that, the more the number of node onsets per unit time, likely it's going to be more arousing. So these are just the top 5 features I'm showing out of the 12. Now for the continuous emotion assessments. So here, as I said, everything is very similar in terms of topology, except for one main difference between this and the global network is I'm taking, so as one bar's features go in, that gets saved as context for the next bar, and that gets input along with the next bar's features. So it's a standard Elman neural network, so one of the basic forms of a recurrent neural network. The training and test set split is exactly the same. It's the same 5 folds of cross-validation. So with that, now we can make a comparison, between these features. How are they changing, and what is it that's more uniform across these two? And have they have some new features crept up? So this is a method that we can use. So the ones on the left are just for the global emotion assessments. The ones on the right are basically for the 1 bar continuous emotion assessments. And over the entire thing, once the network is trained, you can look at the weights and determine these. And then you notice that for valence, a couple of them are still the same. So you still have event density, you still have mode. They changed a bit in terms of their value, the magnitude, or how much percentage they're contributing by. Same thing with arousal again. And you also have a couple of new features that come up. So this is good. What else can we do? I mean, we're still kind of working along these lines to see what else we can do. And one other thing we could do is, instead of taking the entire data set and building one general network, you could now start breaking it by genres and have genre-specific networks. So in our case, metal was the one that showed, a difference across all the other genres. So I had just a metal network, again an 80-20 split, and I could have picked any of these 3, and I decided to go with R&B, just because I like listening to that. These are all, like, I would say, more 70s Motown-ish R&B. Again, after training, now we can plot and the contributions. So again, I'm talking about the top 5 contributing features. So this is for metal, valence on top, arousal below, and R&B, valence on top, arousal below. So arousal seems fine for metal, but when you look at valence, the first thing you notice is the standard errors are so high. Right? And sometimes bad results are actually great for interpreting. So what it tells me is that there is no consistency across these networks. So that could be because of many reasons. Like, first thing is, it's possible that there's a high disagreement because maybe we just need more participant data. There's too much variance now. There's something consistent in metal that we're not getting. Or maybe that's how people feel about metal in general. Like, as a genre, it might not, it might not allow people to come up with consistent ratings. So it could be any of these two, but that's what prompts us to, get a lot more data from participants. Unlike R&B, where you see a lot more consistency, mainly in terms of standard errors. So our goal here was to find the most salient features in audio and how they remain consistent or change as you move from a global assessment to a continuous assessment of emotion. And clearly sophisticated methods already exist, but there's still more that can be done in terms of trying to find, what these features mean, either from a psychological or a cognitive, relevance standpoint. The features are not exhaustive. I think this is still an ongoing thing, both in the MIR community and possibly even in music cognition, on where there are overlaps, how they're actually more unique from each other, where can we get the maximum amount of information. Clearly we need more participant data to find out these universal consistencies and inconsistencies across genres and among listeners. We need more excerpts to increase the size of the data set. So this is kind of like our ideal model, our ideal prediction mechanism, which should also serve as a model, is we should be able to predict emotion judgments taking content from the music as well as from the listener himself or herself, right? So listeners have their own preference, they have their own personality that they bring. One way we can tap into it is physiology, but that in itself may not be enough. That along with maybe something else to do with their preference and personality. And if we have that data now, we have to find ways of maybe clustering these listeners into different groups. That's something of interest to us. Then you could have separate prediction networks for each of these kinds of listeners. That's one way to go. So that's an ideal goal for us. So I want to end finally with this really nice quote, which some of you may have heard, by the famous statistician George Box. All models are wrong, but some are useful. So the idea here being that models are not universal truths, but if we have a good approximation, of real performance, then perhaps we can derive some useful insights. So I'd like to acknowledge all these people who have been very useful for data selection. Selma Sheikh, James McGrath, also our industry sponsor, WebDNA, Web Beckford from WebDNA and Answer. All right, thanks. Yes.
I have a question. What is the overall accuracy during the training and prediction?
Right. So overall, as in
Accuracy.
both together, or just the test? Both together, I didn't see, but I would only look at the test set. Like once the mean squared error was less than the the amount. So let me go back to. I don't have the figures for the continuous one here, but for the global. Let me just go back. Right. So this is what it is for the global assessments.
Another question is that what's the size of the training data set?
Right. So it's 60 excerpts, right? So a 5-fold cross-validation. So 48 for every network. 48 is the size of the training set, and 12 is the size of the test set. Fairly small numbers from an MIR perspective, yes. Yeah, but again, physiology collection is expensive, standardized physiology collection, but now in the day of wearables, hopefully that'll change very soon.
Did you compare your models to any other, maybe simpler or more linear model? I mean, as we talked about before, like local minima are one of the problems with deep learning or neural networks.
Right.
Sometimes like just a simple model might work better.
Right. Typically, that's what we do. Is we would start with something as simple as a correlation, and then go with like a multiple linear regression. It's not been done with this data set yet, but yeah, that's something I would do like for a longer paper or something. We're going to look at that first.
You might want to look at like tree-based models, which could be really interesting for what you're doing here, because they can give you feature importance directly based off the splits.
Okay, so I should talk to both of you guys. later in more detail.
Great. So thanks again, Naresh. Let's take a minute for transition to the last speaker before the break.